G'day, Space Cadets. In this video, I want to talk about a topic which really confused me for a long time. It's something that often gets dismissed as a counterintuitive topic where you just have to trust the maths. I'm talking, of course, about converging-diverging nozzles and the opposite behavior of subsonic and supersonic compressible flows. There are already some really good videos out there which cover the mathematical description of what's going on. I've linked a good video from Josh the engineer in the description, which will help you get an engineering level of understanding. I don't want to repeat too much of that content here. Instead, I want to try and convince you that there's nothing counterintuitive about supersonic flow. I'm not saying that it's simple to understand, but if we take some time to think about the situation in the right way and focus on the fundamental physics, I think we can build an intuitive picture. I'm going to start with a couple of points that may not make total sense to you right now, but keep them in mind as we build up our understanding of the problem. Fluid flows speed up or slow down depending on pressure differences. If a fluid flowing in a pipe has lower pressure downstream than upstream, this pressure difference will cause the fluid to accelerate. If the downstream pressure is higher, the fluid will decelerate. This is also true at the throat of a nozzle. When the nozzle is operating in the supersonic regime, there is a pressure gradient at the throat which speeds up the flow above Mach 1. When the nozzle is operating in the subsonic regime, there is a pressure gradient at the throat which slows the flow back down from Mach 1. Understanding these gradients and how they form is what we will talk about for most of this video. Secondly, the fluid pressure at the nozzle exit must match the environment pressure. This is a fundamental truth like conservation of mass and conservation of energy. The pressure in the nozzle can be lower or higher than the atmospheric pressure at the exit, but then there will be shock waves or expansion fans to enforce pressure equality. Here we have a typical venturi with a gas flowing through it. The flow comes in from the left and moves to the right. As the cross-section area gets smaller, the fluid must move faster to conserve energy and momentum in the system. I'm guessing most of you will be familiar with Bernoulli's principle for incompressible flows, where the total energy of the fluid must be conserved. This means that as the flow speeds up, its pressure drops, and vice versa. The same general idea applies here, but when we talk about compressible flows, instead of total energy, we use properties called the total pressure and total temperature. These values are the pressure and temperature the flow would have if we slowed it to a speed of 0 with no losses. If we plot the total pressure through the venturi, we can see that it is constant everywhere as we have perfect subsonic flow with no friction and no other losses. If we also plot the static pressure, which is what we would measure with a pressure sensor, we can see that it is close to the total pressure everywhere. This is telling us that the fluid is moving slowly and that we can quite accurately treat this flow as incompressible. For this video, we're not concerned with the total temperature, so we'll just skip straight to the Mach number. The Mach number is the ratio of the fluid speed at a particular location to its speed of sound at that same location. Let's plot the Mach number now. As we expected from the pressure plot, we can see that the Mach number is close to 0 everywhere and gets just a little bit higher at the throat. Below Mach numbers of about 0.3, we can treat fluids as incompressible without sacrificing much accuracy. We can't really see anything interesting with this slow flow, so let's speed it up. As we increase the speed, we see changes in both the Mach number curve and the static pressure curve. The static pressure drops a little bit everywhere as the increased velocity converts energy which had previously been stored as pressure into kinetic energy. The pressure drop is particularly noticeable at the throat as this is the point of highest velocity. Eventually, we reach Mach 1 at the throat. Now let's pause and recall the points we introduced earlier. The fluid speeds up or slows down due to pressure gradients. If we consider 2 points in the converging section of the nozzle, we can see that the pressure is higher at point 1 than it is at point 2. Now remember that pressure is really just molecules whizzing around and colliding with each other. The speed of the particles and also the speed of sound in the gas are determined primarily by the gas temperature. A higher pressure means more particles in a given volume and therefore more collisions. the slice of gas between points 1 and 2 will be experiencing more collisions on the left-hand side than on the right-hand side. These extra collisions from the left-hand side create a force which accelerate the slice of gas to the right. Now if we look at the downstream side, we can see the reverse effect happening. The pressure at point 4 is higher than at point 3, creating a net force which is slowing down the slice of gas. This pressure gradient is why subsonic nozzles are subsonic. You might be thinking, wait, we have sonic flow in the throat and an expanding nozzle. Doesn't that mean the flow should be supersonic? Let's recall point 2. The nozzle exit pressure must match the atmospheric pressure. The short story here is that the exit pressure is too high to achieve supersonic flow. In other words, with a high atmospheric pressure, we don't have a large enough pressure difference to achieve supersonic flow. We've primarily used an area contraction to achieve sonic flow, but we also reduced the atmospheric pressure slightly to encourage higher flow velocities in the subsonic regions. Using our knowledge of pressure and pressure gradients, we know that if we lowered the environment pressure even further, we would expect to see higher velocities. Let's do that now. We're going to see some interesting stuff in this animation, so I'll just shut up and let you watch, and we'll chat about what we saw later. As we reduced the atmospheric pressure further, the exit gas velocity increased to compensate for the reduced static pressure. This pressure reduction propagated up the subsonic flow region until the choked flow at the throat. We know that in sonic and supersonic flows, pressure information can't travel upstream. The effect of a downstream pressure reduction when the throat is already choked is to remove the particle collisions from the right-hand side. No particle collisions means no communication method. The Mach 1 flow essentially fills a vacuum to its right. However, the gas particles can still easily interact with those particles above and below them, as they're all travelling at roughly the same speed. We can exploit these vertical particle interactions in order to tell the flow what to do. Instead of communicating via pressure gradients and particle collisions, we instead communicate with the flow via the nozzle shape. As the supersonic flow moves down the nozzle, the area gets larger, and the particles communicate this to each other vertically. Due to conservation of mass, the particles expand to fill the larger cross-section and the pressure drops. From conservation of momentum, a reduction in pressure means an increase in velocity. The flow will keep accelerating as we keep increasing the area. The flow can communicate vertically at roughly the speed of sound, but it's travelling through the nozzle at multiple times the speed of sound, so this vertical communication is really diagonal. This idea is the basis of the method of characteristics, which we may discuss in a later video. This image here was produced via the method of characteristics and illustrates these diagonal communication lines in a typical rocket nozzle. Let's briefly return to the subsonic-supersonic transition animation. Initially, a small region of supersonic flow develops, but then something strange happens. There's a large increase in pressure and a large drop in Mach number, and this happens almost instantaneously at a certain point in the nozzle. As the pressure gets lower, this point gets closer towards the end of the nozzle. This strange effect is a normal shock. Neither the supersonic or the subsonic expansion alone can match the nozzle exit pressure with the atmospheric pressure, and so a small amount of both is needed. A normal shock is nature's way of transitioning between the two flow regimes. Let's detour for a minute and have a quick chat about normal shocks. I think everyone watching this video is probably already familiar with the idea of shock waves forming around a supersonic aircraft. The aeroplane is moving faster than the speed of sound, so the air can't get out of the way and piles up, creating a shock wave and a region of high pressure behind the shock wave. We're interested in the part of the shock wave that forms at the very tip of an aircraft's nose or wing leading edge. Here the shock wave is perpendicular to the direction of motion of the aircraft. This kind of shock wave can also occur in tubes and nozzles, as we saw before. The flow behind a normal shock wave is always subsonic. The faster the plane goes, the more air piles up and the higher the pressure behind the shock becomes. A higher Mach number means a bigger pressure difference. This is easy to understand from the point of view of the aircraft where the shock wave appears stationary, but consider what this situation would look like to someone standing on the ground. To them, the aeroplane and its shock wave are moving. To the observer, a higher pressure difference across the shock means a louder boom and a shock that travels past them faster. Higher pressure differences create shocks that travel faster. This is an important point for our nozzle example. One final note on shocks. They are an inefficient compression process and we lose a lot of energy across a normal shock. If you were paying close attention to our transition example before, you would have noticed that the total pressure in the nozzle dropped sharply when there was a normal shock present. And the higher the Mach number, the greater this total pressure loss. In this intermediate expansion situation, we only have a small region of supersonic flow. If we continued the supersonic expansion all the way to the nozzle end, we would have about a Mach 4 flow. But the nozzle pressure would be much lower than the atmospheric pressure, which is still quite high. In fact, this large pressure difference would correspond to something like a Mach 6 shock. A Mach 6 shock in a Mach 4 flow would travel up the nozzle at about Mach 2. While pressure information can't transmit up a supersonic flow via traditional particle collisions, normal shocks can propagate up supersonic flows. This Mach 6 shock would move up the nozzle, and the pressure immediately before the shock would increase as the amount of supersonic expansion prior to the shock has decreased. The pressure difference across the shock is now smaller, making it a weaker shock, which would travel slower. As it continued propagating up the nozzle, it would travel slower and slower until it reached an equilibrium point where it stops moving. At this equilibrium point, the supersonic pressure drop, shock pressure increase, and subsonic pressure increase combined would match the nozzle end pressure with the atmospheric pressure. It's important to note that the shock doesn't affect the flow properties in the supersonic flow region. Only the shape of the nozzle can do this. The shock position simply determines where the supersonic flow region ends. As the exit pressure is reduced, this lower pressure information can propagate up the subsonic flow section until it reaches the shock. With a lower downstream pressure, the pressure differential across the shock has been decreased, making it a weaker and slower shock, and so it will move down the nozzle until it finds a new equilibrium point. Eventually, the shock will reach the nozzle exit. If we reduce the pressure further, the pressure difference becomes too small for a normal shock to exist, and we will transition into two-dimensional oblique shocks and fancy shock structures like Mach diamonds. I haven't animated these here for simplicity, but the end result is that the flow doesn't slow down as much as it would have for a normal shock. Eventually, we reach a perfectly expanded nozzle with no shocks anywhere. Finally, I want to address one last confusing point. Why can't we increase the Mach number above 1 by contracting the throat area further? We'll work through a couple of examples to understand this. First, let's consider a choked converging nozzle. If we suddenly removed part of the converging section, we would create a large pressure difference between the subsonic flow at the new throat location and the atmospheric pressure. This pressure difference would quickly accelerate the throat flow. As the throat flow is initially subsonic, this low pressure would propagate back up the flow as a low pressure pulse and increase the flow speed everywhere. If the total pressure is high enough, we will still achieve choke flow at the throat, but now with a larger area and higher mass flow rate. Now let's consider what would happen if instead of increasing the throat diameter, we decreased it. The accelerated flow would be supersonic and have reduced pressure at the exit. The environment pressure would need to be modified to prevent shocks from forming at the exit. However, the real problem here is that we can't have converging supersonic flows without shocks forming. Whenever supersonic flow streamlines are turned into themselves, a shock will occur, and these shocks are known as oblique shocks. Remember that in supersonic flows, the particles can't communicate back up the stream and warn the incoming particles that they will need to change direction soon. Instead, the particles continue straight until they collide with the deflected downstream flow. The particles pile up, this time creating an oblique shock. Oblique shocks are weaker than normal shocks as the flow is simply being deflected a little bit, rather than almost completely stopped. A supersonic contraction and the resulting oblique shock waves are exploited in supersonic wind tunnel diffusers to gradually slow a supersonic flow and increase its pressure back to ambient without needing a strong normal shock. We can clearly see in our image that the streamlines are converging. If these flows were supersonic, this convergence would cause shock waves to form. However, our flow is only sonic, and so an infinitely weak shock wave would exist temporarily. In reality, it would not get to the point where supersonic flow and shocks existed, as a high pressure pulse would propagate up the nozzle to slow the flow. We would achieve choke flow again at the throat, but with a reduced mass flow due to the smaller area. I would like to conclude this video by reiterating a few key points. Subsonic nozzles have a pressure gradient at the throat which decelerates the flow, while supersonic nozzles have a pressure gradient at the throat which accelerates the flow. A high total pressure and an area contraction are required to generate sonic Mach 1 flow at the throat. We can't accelerate flows above Mach 1 with an area contraction alone. A low atmospheric pressure and an area expansion after the throat are required to generate supersonic flow. We can communicate down a supersonic flow with particle interactions, but not up the flow. Instead, we can communicate the desired behavior of a supersonic flow via the nozzle geometry. Normal shocks can travel up a supersonic flow, but they can't influence the properties in a supersonic flow region. A normal shock can only terminate a supersonic flow region. A subsonic nozzle can be thought of as a special case of supersonic flow where the normal shock has progressed all the way to the throat and then disappeared, leaving subsonic flow everywhere. That's all for this video. Please leave any comments or questions you have in the comments section and like and subscribe if you enjoyed this video.